Okay, thank you. Hi, everyone. I'm Alberto Carlo Maria Mancino, a second-year PhD student. And for me, it's an honor to be on this stage to present KGTORe, tailored recommendations through knowledge-aware GNN models. I'm grateful to my co-authors and colleagues from the SysInflab laboratory at the Polytechnic University of Bari for their contribution and dedication to this work. In our work, we propose KGTORe, a recommendation model that is based on three main components: content information coming from knowledge graphs, a user decision modeling, and a graph-based architecture. Our main intuition is that each user-item interaction results from a specific user decision process, and that the motivations behind this process can be found in the rich semantic features coming from knowledge graphs. So we embedded these intentions in our model, and combining the semantic representation of items and the user decisions, we integrate them in a graph-based architecture, exploiting their ability to collecting information from multi-hop neighbors and the competitive performance in recommendation. But we are not the first that try to use intentions to model the user behavior. In fact, state-of-the-art solutions say that each user, when interacts with all the items in the catalog, it is by means of a set of intentions. And these intentions are shared between all the users in the system. Moreover, these intentions are not explicit and learned in an end-to-end fashion. Instead, we think that each user-item interaction is unique, and it is driven by specific intentions. So we use these intentions not only to explicitly interpret the edge between a user and an item, but also to drive the training of the recommender. So now we see how we build these semantic features. Like in classic knowledge-aware models, we state that each item is rated with an entity in the knowledge graph, and this entity is linked with other entities by means of with a predicate. So each item in the catalog is described by the set of the tuples predicate object related to the entities directly linked to the entity of the item in the knowledge graph. In this example, we can see Mrs. Doubtfire, which is an item in the catalog, but also an entity in the knowledge graph. And it's linked to Chris Columbus by the predicate directed by, and to Robin Williams by the predicate starring. So the final description of the item is the set of the tuples starring Robin Williams and directed by Chris Columbus. So now we are ready to see how we modeled these user decisions. So we consider that we don't need to take into account all the semantic features in the item description, but to select the most relative ones. To do so, we consider the binary feedback of the user, and for each positive feedback, we pick a negative one, like in classic pairwise approaches. Then we find the most discriminative features by using a decision tree that discriminates positive from negative interactions by means of semantic features that could be present or absent in the description of an item. In this example, we can see a user that really likes Harry Potter, and this could be for the presence of Chris Columbus as director. But if you look carefully, this user is more influenced by the presence or the absence of Johnny Depp starring in a film. In fact, if Johnny Depp is starring, the user will discard that movie for sure. So the final intention considers not only the presence of Chris Columbus, but also the absence of Johnny Depp starring. So for each decision tree, we build the user intention at the user decision path that leads to that item. And so the final intention is a combination of present or absent features. And we assign a positive sign if they are present and a negative one if they are not. In this way, assigning a latent representation to each feature, we can combine them to build the representation of the user intentions. In fact, the overall intent is a combination of the embedding of the features in the decision path. If you look at the example on the left, you can see that the user decision for Harry Potter is the combination of the positive representation of the embedding of Chris Columbus and the negative representation of the embedding of Johnny Depp. So now we are ready to build the final content representations of user and items. Regarding the items, this embedding is just the combination of the features in the item description. While for the user, this embedding is the combination of the knowledge-aware decision embeddings that we have seen in the previous slide. So we have seen how to build this, but it's also worth to notice that they share the same space, that is the feature space, because they are derived from them. We then also have taken into account the collaborative signals. So we built the user and item collaborative representations and trained them like in LightGTN, which is a very simple but effective approach. Then the final representation of user and items that we named holistic representation is a weighted summation that balances the contribution of the knowledge and contribution of the collaborative signal. We can see that alpha and beta are respectively the weight for the item and the user representation. So now we can see how we built our experiment part, and that we use to empirically prove that KGTORe is competitive with our baselines. We use 3 datasets. They are well known in the recommendation field, and we use DBpedia as knowledge graph. We considered just implicit feedback, and we filtered both the dataset and the knowledge graph. We think that reproducibility matters. So if you are interested or just curious in this work, please check our repository, and there you will find all the instruction and the source code that we use to perform our experiments. And then you will find also our baselines that are listed here. In particular, for the knowledge-aware ones, we consider those that use the same semantic feature representation that we used, while for the graph-based one, we consider LightGTN that, as I said, shares the construction of the collaborative signals, DGTF, which uses intention, and KGIN that combines both intentions and the knowledge. Here you can see the performance of KGTORe in terms of accuracy. As you can see, it is competitive with all the baselines over the all 3 datasets. If you are interested in more information about this, please check our paper. But we are also interested in check if KGTORe is also able to address the cold start issue. So we divided the dataset in 4 quartiles, considering the number of interactions for each user, and then we built these 4 groups, from the coldest user to the warmest. We then measured the NDCG for all the baselines, and as you can see, KGTORe is able to address this issue, but also when the information increases, so when the users become warmer and warmer, it is able to better leverage the amount of increasing information for each user. So it's more able to build user intentions. We also ask us if our contributions are really impactful. So we, first of all, we try to vary the contribution of alpha and beta, so the balancing between the knowledge and collaborative signals. Regarding the users, we have found that the content information helps, but when it not overcomes the collaborative one. Instead, for the items, we discovered a completely opposite behavior, where the content information, so the feature in the item description, are more relevant than the collaborative signals. We also tried to understand if our decision trees really works. So we tried two different methods. We use the shuffled decision trees, so we retained the original feature selection of the decision trees, but then we shuffled the user intentions. Then we also tried to randomly assign to each user a set of features for intentions. And as you can see, the performance dropped in both cases. But when the feature selection is retained, so in the shuffled one, you can see that the performance are better than the totally random one, where the totally random coincides with a basic collaborative model. So in conclusion, we found that KGTORe is able to exploit the explicit semantic features and to use them to characterize not only the items, but also the user decisions in a graph-based recommender. In future works, we are interested in finding new approaches different from decision tree to find the user intentions and to use different kind of set information. Moreover, we are starting new experiments on larger datasets to test our model and baselines, and we are also looking for new ways to integrate the knowledge representation of items and user decision in the training of a recommendation model. It was a pleasure for me to present our work. And if you are interested in this work, please don't hesitate to contact us. Thank you.
Thank you, Alberto. Do you have any questions? You can come to the microphone, and in this while, I'll start with the first question. Okay, in the ablation study, you analyzed the impact of alpha and beta. Okay, they should be the trade-off coefficients for knowledge and the collaborative information. So, you defined two different coefficients for users and items. So, have you investigated if there are any significant or substantial differences between users and items?
Yeah, absolutely. As I mentioned here, both the user and the items have two completely different behaviors. In fact, we find that for the users, the collaborative signal is more informative. So we cannot let the knowledge part overcome on the collaborative one. I think also because for the items, the semantic representation is more rich of information compared to the user, where the collaborative information is a lot important. And so, as I said, for the items instead, we found that the content representation really increases the performance. So we have to boost it during the training.
Okay, thank you. We have a second question from Slido that is connected to this. So, what were the final values used for the weights, alpha and beta?
If I remember well, for beta it was around 0.3. Instead, for alpha it was around 0.8. So there are exactly two different values. A very high value for the items, so a lot of contribution of the knowledge. Instead, for the user, it is just like a way to interpret the user decisions, but without dropping the collaborative signal.
Okay, thank you. And I have another question. Do we have any questions from the live audience, let's say? Okay. So I can continue. I read in your paper that you showed like a table in which you showed the affinity number, okay, between a specific user, I don't know if it is a test user or something like that, and their features. And that is obviously connected to the interpretability of the method, and that's interesting. But in plain words, how should we interpret those affinity numbers that we are seeing there? How can we use them?
Yeah, that is, in my opinion, a very interesting part of the paper, but we don't added it to the presentation because of the limited time, because we cannot say that that KGTORe is interpretable. It uses explicit features, but then the feature embeddings are trained during the training of the recommender. So for this reason, we try to understand if the training is able to preserve the semantic meaning of the features. So we try to find if the user preferences are in some way correlated with the embeddings of the features. And the interesting part is that user feature and item embeddings share the same space, so share the same latent features. And for this reason, we can compare them very easily. So we are also interested in finding new way to exploit these embeddings and maybe finding a better way to interpret the result.
Okay, let's thank our presenter.